Good day, everyone. Today we'll focus on permutations and combinations. These fundamental concepts are crucial in probability and statistics. Let's explore how they work and their applications. To start, counting is a fundamental mathematical concept that is used to determine the number of ways events can occur. It's essential in probability, statistics, and many other fields. Today, we'll cover the core principles and their practical applications. Before diving into permutations and combinations, let's cover counting rules. The first is the multiplication rule, which tells us that if there are n ways to do one thing and m ways to do another, then there will be m times n ways to do the both. For example, we have a 4-digit PIN code on our phone. Each digit can be either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. How many different PIN codes can we create? So since each digit has 10 different possibilities, and we have 4 places for the whole PIN code, we have 10 times 10 times 10 times 10, or 10 in the 4th power, which is equal to 10,000. So there are 10,000 different PIN codes we can create. Next, we have the factorial rule. We define the factorial of a number n as the product of all positive integers up to n. For example, 4 factorial equals to 4 times 3 times 2 times 1, which is 24. Factorials are very important in counting because they help us calculate permutations and combinations that we will discuss later. So what factorial rule is used for is to find total number of possible arrangements of n distinct items where the order matters. For example, let's say we have 3 balls of different colors, red, blue, and green. We want to arrange them in all possible ways. How many ways can we arrange them? Well, one possibility is red, blue, green. Another one is red, green, blue. Then blue, red, green, and blue, green, red, and finally green, red, blue, and green, blue, red. As you can see, none of them are repeating, and we have total of 6 possibilities. So we have 3 balls and 6 outcomes. How can we come up with the formula to calculate all different arrangements? We have 3 places where we can put our balls. If we look at the first place, there are 3 different balls that we can put in that place. So we can put either red, blue, or green into the first place. Then we have 2 spaces left and 2 balls left. So how many different balls can we put on the second place? 2, either blue or green. And for the last place, there's only 1 left ball that can be placed there. So by the multiplication rule, we have 3 times 2 times 1, which is 3 factorial, and this is equals to 6. Now let's move on to permutations. A permutation is an arrangement of objects in the specific order. This concept is important when the order of items matters. For example, as before, we have now 5 balls of different color, but we still have only 3 places. We want to find how many permutations possible. So for the first place, we have 5 different balls we can put in. Then we have second place, 4 different balls. And for the last place, only 3 different balls left. So we have 5 times 4 times 3, which is 60. Now, if we write it as 5 times 4 times 3 times 2 times 1, and divide it by 2 times 1, we already know that the numerator is 5 factorial, but the denominator is 2 factorial. And the answer will be the same, 60. Now, another example is arrange 7 books on the shelf that can fit only 4 books. Again, how do we do that? First place can be occupied by one of 7 different books. Second place by 6 different books. Third place by 5 different books. And last one can be occupied by 1 out of 4 remaining books. So we have 7 times 6 times 5 times 4. Again, we can present it as 7 factorial, but we need to divide it by 3 factorial to be the same. So we have 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. If we compare these two examples, it is easy to see where 5 and 7 came from. But it's not easy to see where 2 factorial and 3 factorial came from. But we know that 2 is 5 minus 3, and 3 is 7 minus 4. So we can present 2 factorial as 5 minus 3 factorial, and 3 factorial as 7 minus 4 factorial. And now we can look at the formula for permutation. It is n factorial divided by n minus r factorial, where n is the total number of items and r is the number of items to arrange. So we have it. So we see in our example that n is 5 in the first example, which is 5 different balls, and 3 is the number that we need to arrange. And for the second example, we have 7 total books, which is n, and we want to arrange 4 of them. So r is equal to 4 in this case. Sometimes we encounter situations where some items are the same, and we need to account for these repetitions. The formula for permutations with identical items is n factorial divided by r1 factorial times r2 factorial times rk factorial, where n is the total number of items as before, and r1, r2, and rk are the counts of each identical item. For instance, let's consider an example involving the letters in the word balloon. The word balloon has 7 letters total, so that's our n. And we see that L appears twice and O appears twice. So this is going to be our R1, R2. Using the formula, we calculate the permutations as 7 factorial divided by 1 factorial times 1 factorial times 2 factorial times 2 factorial times 1 factorial, where 2 factorial is for L and another 2 factorial is for O being twice. So this is equal to 1,260 possible unique arrangements. So we use this method to correctly count the number of distinct ways to arrange items when duplicates are involved. Now let's shift our focus to combinations. Unlike permutations, combinations are used when the order of selection doesn't matter. The formula for calculating combinations is n factorial divided by r factorial times n minus r factorial, where n is the total number of items and r is the number of items to choose. As we can see, the difference between the formulas is r factorial in the denominator for combinations. This is because we need to address that the order doesn't matter, unlike in permutations. So let's look at the example. For instance, we want to choose 4 friends out of 6 to invite to a party. We do not care in what order we invite them. We care who we invite. So we start with permutations. We choose 1 friend out of 6 to invite first, then 1 friend out of 5 to invite second, then 1 out of 4 for the third spot, and the last choice we select among the remaining 3 friends. Now, since we don't care about the order, we need to count the number of ways we can arrange our things in our places, which is 4. The same as we did the factorial rule. So it is 4 times 3 times 2 times 1, which is 4 factorial. And this is our r, according to the formula that we need to divide by our permutation to address the fact that the order doesn't matter. So that's how the formula for combinations and permutations is different. Now, next example for the combinations is selecting 5 numbers out of 39 for the lottery ticket. Again, the order doesn't matter, so we choose the number among available 39 numbers as our first choice. Then 1 number out of 38 remaining for the second spot, and so on until we fill up all 5 spots. So we get 39 times 38 times 37 times 36 times 35. And we know that it is the same as 39 factorial divided by 39 minus 5 factorial, as we calculated the permutations. But since we said that the order doesn't matter, we also divide by the number of ways these 5 numbers can be arranged in 5 spots, which is 5 factorial. Thus, we see that it is the same as the given formula 39 factorial divided by 5 factorial times 39 minus 5 factorial, where 39 is an n, the total amount of numbers we can choose from, and 5 is an r, which is the amount of numbers we choose for the lottery to play. Now that we've covered both permutations and combinations, let's highlight the key differences between them. The primary distinction is that permutations consider the order of items, while combinations do not. This means that permutations are used when the sequence matters, such as arranging books on the shelf or determining the order of winners in the race. In contrast, combinations are used when the sequence is irrelevant, such as selecting team members or picking lottery numbers. The formulas also reflect this difference. Permutations use n minus r factorial to account for the order, while combinations include r factorial to eliminate repeated counts of the same set in different orders. To better understand how these formulas can be used, let's look at some practical examples. Consider a task of creating a secure password. If you have 26 unique letters of the alphabet and need to arrange 4 of them for the password, assuming we use each letter only once. So how many different possibilities we can have? It is 26 factorial divided by 26 minus 4 factorial, which is 26 factorial divided by 22 factorial. Now we write 26 factorial as 26 times 25 times 24 times 23 times 22 factorial. And we stop at 22 factorial because this is the same number as in denominator, so we can cancel these two numbers. And we end up with 26 times 25 times 24 times 23, which is equal to 358,800. Another example is organizing a lineup for a race. The order in which the runners finish is important to determine the winners. If there are 5 runners and you need to determine the order in which the top 3 finish, so the number of possible lineups is 5 factorial divided by 5 minus 3 factorial, which is 5 factorial divided by 2 factorial. We write 5 factorial as 5 times 4 times 3 times 2 factorial, and we stop there because we can cancel 2 factorial in numerator and denominator, and we have 5 times 4 times 3, which is 60. Now for combinations, one common scenario is selecting cards from a deck. If you're drawing 5 cards from a standard 52-card deck, the combination of cards is what matters, and not the order in which they're drawn. So the number of possible combinations is 52 factorial divided by 5 factorial times 52 minus 5 factorial, which is 52 factorial divided by 5 factorial times 47 factorial. Now we write 52 factorial as 52 times 51 times 50 times 49 times 48 times 47 factorial. And we stop there because we see that we can divide by 47 factorial to cancel them both in numerator and denominator. We also want to write 5 factorial as 5 times 4 times 3 times 2, and we don't write times 1. And now we can see that we can reduce 5 and 50, and we can reduce 4 and 48 by 4, so we get 12 in the numerator there. So we end up having 52 times 51 times 10 times 49 times 12 divided by 3 times 2. And we see that we can reduce even further because 3 times 2 is equal to 6, and 6 and 12 can be reduced by 6. So we have 2 in the numerator for 12, and we have 52 times 51 times 10 times 49 times 2, which is 2,598,960. Another example is choosing flavors for an ice cream sundae. If an ice cream shop offers 12 different flavors and you want to choose 3 different flavors for your sundae, the number of possible combinations will be 12 factorial divided by 3 factorial times 12 minus 3 factorial, which is 12 factorial divided by 3 factorial times 9 factorial. So we can write 12 factorial as 12 times 11 times 10 times 9 factorial, and we stop there because we can cancel it with 9 factorial in the denominator. And then we write 3 factorial as 3 times 2, and we can again reduce it with 12 by 6 to get 2 in the numerator. So we have 2 times 11 times 10, which is 220. So you have 220 possibilities you can arrange your ice cream sundae. In summary, we've explored the fundamental concept of counting, focusing on permutations and combinations. We've discussed how permutations are used when the order of items matters, and combinations when the order doesn't matter. We also covered the basic counting rules, the factorial rule, and practical examples to illustrate these concepts. Now, thank you for your attention, and I hope this presentation has provided you with the clear understanding of these counting techniques. Thank you.